Hello everyone, welcome back to Diksha Karnataka YouTube channel, and you are watching Decode NCERT test series, Decode NCERT series, where I am trying to explain you the chapters part that you have are important for your PO preparations as well as any competitive exams that you may be preparing for. And today is the part 1 of electrostatic potential and capacitance. Why part 1? Because this is a very long chapter and I don't want to waste too much of your time because already NCERT is boring, so you might feel bored. Okay, sir is taking a too long of a class, so I have decided to break it into two parts. Today is the first part, second part I will be discussing on Tuesday's class, right? Now let's start with this chapter, electrostatic potential and capacitance. So in the first part you can just read it. The most important part starts from here. Okay, so if you remember, in your first PU you have learned about work done, right? Also later on via work energy theorem you have linked them with energy as well, okay, kinetic energy and somewhat potential energy as well. So here also, as you can see, work done by external forces moving charge from say a point R to P is given by WRP is R to P F external dot dr, and they have taken a negative sign R to P, now they have reversed it, and F external dot dr. Okay, this work is done against the electrostatic repulsive force and gets stored in the potential energy. Sign negative means it is getting stored, okay, as an electrostatic potential energy, and the force is repulsive in nature. Okay, so dr and f they are in opposite direction, then there will be a negative sign. Okay, even though that is not clearly explained, that's why I am here, I am adding whatever extra part that you need to know. At every point on electric field, a particle with the charge q possesses a certain electrostatic potential energy. Now you have to be careful here, it is not electrostatic potential. Potential is a different thing, we will learn about it in a while. Not a super different thing, just a different, there is a definition for that as well. But here what I am trying to emphasize on this, that with the charge q, the charge q is very important, okay, possesses a certain electrostatic potential energy. So if there is a electric field, if there is a charge q, there will be associated electrostatic potential energy. Now thus potential energy difference delta U is basically given by UP minus UR is equal to WRP. So work done is basically difference in potential energy. So each and every point there is a potential, right? Here it has a potential energy, here it is a potential energy, and if you move it from here to here, you are doing some work. So that work is basically the potential energy difference. This is very important. Okay. Now what else? These parts you can skip. Depends only on the initial and final positions of the charge. It means that the work done by the electrostatic field in moving a charge from one point to another depends only on the initial and final points and independent of the path taken. So it is not dependent on the path, right? So from there we can, so the right side equation depends only on the initial and final position of the charge. It means that the work done by the electrostatic field in a moving a charge from one point to another depends only on the initial and final points, and it is independent of the path taken to go from one point to other. This is the fundamental characteristic of a conservative force. So conservative force means if you start from here and suppose you take the charge from here to here, like this path. Your friend said, okay, I want to take the shortcut, I want to take this route. Okay, I said, okay, let me try this route. Excuse me. The right side of equation 2.2 depends only on the initial and final positions of the charge. It means that the work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points and is independent of the path taken to go from one point to other. This is the fundamental characteristics of a conservative force. So we have already understand that electric field is a conservative field, electric force is a conservative force, and there are one more force which is conservative, if you know, just mention that in the comment below. There is a conservative field as well as conservative force associated with it. If you know the answer, mention in the comment below. You know the answer obviously, but maybe you may not be able to link it here. So what is the meaning of this? Suppose this is the point A, this is the point B, and you are taking a charge. This is an electric field present somewhere, and you are taking a charge, say, along this path. Your friend says, "Now I want to take this path." Another friend says, "No, I want to take this path." And one of your naughty friend, he said, "No, I will take path like this." Now, in which of these cases the work done is minimum, work done is maximum? So, according to this, that if the force is conservative, field is conservative, then definitely it does not matter through which path you have taken. All the paths are equivalent and the work done is same, no matter what path you have taken, right. So, this is the basic meaning of this paragraph, and electric field is conservative field, electric force is conservative force, that is also indirectly been told here. Now, let us move on. Now, here potential energy difference in terms of physically meaningful quantity is work. So, as I said, potential energy is always defined in terms of work. A convenient choice is to have the electrostatic potential energy at 0 at infinity. So, electrostatic potential is 0 at infinity, that is the choice. So, we have to take consider a point where electrostatic potential is 0. So, the most convenient way to define that is at infinity. So, at infinity the electrostatic potential energy is 0, and if you bring the charge from infinity to that point on electric field, the work that you do is the potential energy of that particular point. Okay. So, from infinity to point A, that is the potential energy of point A. From infinity to point B, that is the potential energy of the point B. Now, A to B is the potential difference. So, these are the three things that you have to remember: absolute potential energy and potential energy difference. Okay, most of the cases potential energy difference is important, but sometimes absolute potential is also important. So, potential energy of a charge q at a point is the presence of the field due to any charge configuration, is the work done by the external force in bringing the charge from infinity to that point, right. Now, electrostatic potential, work done by external force in bringing unit positive charge from R to P is given by Vp minus Vr divided by Up minus Ur divided by Q. So, electrostatic potential, which is I told you already that it is different from potential energy. Potential is basically potential energy per unit charge. So, it is a fixed quantity, it does not vary, does not depend on the charge, because you have said it is only due to one positive charge, unit positive charge. So, if you define it, and definitely it is a constant quantity, unlike potential energy that can vary depending upon, suppose you are choosing 10 coulomb charge or 5 coulomb charge or 50 coulomb charge. Based on the charge, electrostatic potential energy will change, but electrostatic potential at some point will remain constant. Okay, and we choose, as like potential energy, we choose the potential to be 0 at infinity. This is also important line. Next is so if you see this diagram, I have already drawn a similar diagram like this. This is another diagram. They have shown that electric potential is also independent of path. Now, potential due to a point charge, the derivation is super important. This diagram you have to draw, and these are the steps that you have to do to do the derivation. Derivation I have done in my class, in my Brahmastra class. You can check that out, or if you are studying it from the book, you have to remember these are the steps that you have to follow. This graph is important, the nature of this graph. So, as you can see, electric field is initial value of electric field is very high compared to electric potential. So, if you see, electric field is starting somewhere here. So, initially electric field has a higher value, whereas potential has a lower value, right. So, this is potential B, this is electric field E, but as this is going, okay, electric field is going to the 0 rapidly, more rapidly compared to electric potential. This is the electric field line. It is starting with a higher value, but it is going to 0 much more rapidly compared to electric potential. Electric potential starting at a slightly lower value, but it is going to 0 much slower than electric field. Okay, that is the basic thing. So if you start at high, you go to 0 quickly. If you start slightly lower, you goes to 0 slightly slowly, right? Now let's move on. So, the electrostatic potential varies 1 by r and electric field varies 1 by r square. So, this is a question for KCET, that electric field and electric potential varies as 1 by r square, 1 by r square, 1 by r cube, like that. Okay. So, this is very important thing to remember, okay, and this might come as an objective for your PU board exam as well, that directly from the book. Now, let us move on. Potential due to electric dipole. This is also important in a sense that this formula is important, the final formula is important. Okay. Derivation, you can check this derivation, but this is a slightly complicated derivation in my opinion, even though this derivation is not important for PU board exam, but if you still need the derivation, you can mention it in the comment below that sir, I want this derivation, and if I receive enough comments, I might incorporate this derivation in our next lecture before going through the next part. Okay, this is the first part, right? Part 2 I can incorporate this derivation before starting the lecture. So, mention that in the comment below, sir, I want the derivation, then only I can incorporate that. Okay, but this derivation I do not want you to follow, this is not super important for your PU board exam. Okay, final result is important. Final result is important for PU board. Final result is important for obviously any competitive exam as well. Now, as you can see, electric potential is basically proportional to 1 by r square. So, V is equal to 1 by 4 pi epsilon naught P dot r by r square. So, this is also a point of question for KCET, not for PU board. PU board generally chapter wise question comes, but here this question once asked was that the electric field and electric potential for a dipole is 1 by r cube for electric field and 1 by r square for electric potential. So, be careful. Normally for a single charge it is 1 by r and 1 by r square, but for a dipole it is 1 by r cube and 1 by r square, right. Let us move on. Potential due to system of charges. In potential due to system of charges, what you have to do, you are trying to find potential at some point P and there are a lot of charges present. So, potential, what you have to do, you have to calculate the potential due to individual charges at this point, okay, and then add them up. Simple scalar addition, because potential is a scalar quantity, okay, and its unit is volt, obviously, as you know. Okay, so that is how this potential you can calculate. So, that is a easier way to calculate the potential. Okay, and in terms of formula, this is the formula, you can remember this formula, or if you remember the concept, that is also fine, helpful for solving numerical questions. Now, another important concept from this chapter, equipotential surface. What is equipotential surface? Equipotential surface is the locus of all the points having same potential. What is the meaning of locus? Locus means if you join using a line or using a circle or using a sphere or using a continuous surface, okay, if you join all the points having same potential, same value of potential, then that plane, that line is called locus. Okay, if you have studied the curvilinear coordinate system, where you have studied about ellipse, hyperbola, parabola. So, there the definition starts with locus of this, locus of that. So, locus means if you join all the points, that is the locus, right. Here they have given you the statement that equipotential surface is the surface with a constant value of potential at all points on the surface. So, all point on the surface has constant potential, that is equipotential surface. Equipotential surface can come as an objective, can come as an 2-mark question, can come as a 3-mark question. So, it is very, very important concept. For a point charge, as you can see, for a point charge, the equipotential surfaces are concentric spheres. Each single sphere has same potential on all the points, but the sphere next to it it is also an equipotential, but these two spheres have different potentials. That is also important to understand. This potential and this one, even though they have they are equipotential surfaces, these two have different potentials, but all the points on this circle itself has the same potential, right? Clear? So, point charge is important. Positive charge, negative charge, no matter what is, if it is point charge, it will be concentric spheres. Now, for any charge configuration, equipotential surface through a point is normal to the electric field at that point. So, equipotential surface is basically normal to the electric field. This direction is important because objective questions have come from this concept, and that might come from this concept as well. So, they might say the equipotential surface is tangential to electric field, parallel to electric field, perpendicular to electric field, none of the above. So, perpendicular to electric field, perpendicular means normal, normal is perpendicular. So, you have to mention it is normal to the electric field or perpendicular to the electric field. Okay. There is no potential difference between any two points on the surface, and no work is required to move a test charge on the surface. So, this is also a point of objective question. What is the work done to move a point charge on an equipotential surface? That is 0. Okay, because all the points have same potential. Same potential means no work is being done. Okay, potential difference is 0. Potential difference times charge is the work done. So, that is not there. So, that means the work done to move a charge in a potential is 0, right. So, this is a diagram, you have to draw this diagram. This is for a dipole, okay, and two identical positive charges. So, for dipole they are also concentric circles, but there will be some overlapping, and after this is the simplest diagram. After this, the diagram becomes little bit complicated. For positive charge this is okay, okay. This is simple, you can draw that. Now, this is derivation is also very important. Only one thing I have to ask you to change is this. You have to change this plus sign to negative sign. Okay, let me do it. V minus delta V. If you are using delta V or dV, does not matter, but this will be minus sign, okay, because electric field always points from higher potential to lower potential, but here they have given such that electric field is pointing from a lower potential to a higher potential, which is technically wrong. Okay, that is why I ask you to change it, and in this derivation step, what you have to do? You have to do final minus initial, that we know, right? Final minus initial, so it will be minus delta V automatically. Instead of doing this way, you can do it like this way. Okay, this is, I feel, is easier to remember. Not only that, this will also remove any confusion that you might have. Okay, to show that this is negative, they have done the opposite way, and they have defined it, written it a lot of things for that, but you can skip that and you can simply mention that let us consider two equipotential surfaces, one kept at V, one kept at V minus delta V. Then to move a charge from V to point A to point B, then we can write the work done is basically E dot delta L is equal to final potential minus initial potential, then you will get a negative sign automatically. You do not have to put it on the wrong way, right. Now, let us move on. So, this is the formula. Normally, for solving numerical problems, we will generally consider E is equal to plus B delta V by delta L. Sign does not matter, but while doing the derivation, the negative sign has to be there. Okay, be careful. Derivation time negative sign has to be there if you are solving any problems in competitive examination especially. Okay, then plus sign, you can take it plus sign and calculate the magnitude, because 99% of cases they will only ask you to calculate the magnitude of electric field, calculate the magnitude of electric potential. So, magnitude wise this is fine. Now, electric field is in the direction in which the potential decreases the steepest. So, as I said, they have drawn the diagram wrong, but in the statement they have mentioned it correctly. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at that point. So, that is the definition. Electric field is basically change in electric potential divided by the distance between two consecutive equipotential surfaces. Now, one more thing, based on this statement that electric potential decreases the steepest in the direction of electric field. So, suppose they give you a question, a HOTS question based on this, is that there are three parallel electric field. Okay, there are 3 points, point A, point say B, and say point C. Now, where will be the electric potential be maximum? Okay, so which one is maximum, VA, VB, or VC? Now, you know that B is between A and C. So, B is obviously not a choice. It will be either A or C. So, you have to understand that electric potential is always lowest closer to the electric field. So, this is the direction of electric field. So, electric field slowly electric potential will decrease. So, as you are moving from left to right, when you are facing this from left to right, electric potential will be highest on your left hand side and maximum on the right hand side. So, electric potential of definitely VA is maximum, VC is minimum. Okay, in this case. So, VA will be the maximum for these 3 points, okay, and VC will be minimum for these 3 points, because electric potential always decreases in the direction of electric field. So, this is the basically a HOTS question that you might face while getting the question, right. Now, scroll. So, this is another formula. When 3 charges are kept at some different distances, then the system will itself will have a potential energy. This is not potential, this is potential energy. So, basically suppose you have 3 charges, 3 charge configuration, okay, they may have a stable potential energy. If you want to disturb that piece, you have to offer some extra energy from outside. Okay. So, basically in that case potential energy will be negative. If the potential energy is positive, then they are not stable, they want to disperse from each other. Okay. So, 3 charges separated by some distance, potential energy, this formula is helpful for numerical questions, this formula is helpful for your competitive exam questions as well. So, based on this formula, lot of questions came in not only for PU, but for also competitive exams. Now, this is one example that I suggest to check if you want to consider that how we are applying this formula to calculate the potential at the center of this charge Q naught. You can check this out, it is slightly longer, but simple to solve, understand. Okay, some cases it will be 0, some cases it will not be 0. So, you can check this out and you can figure it out yourself. If you face any difficulty, you can check my KCET lecture series, I have done this solution in there. Now, potential energy of a single charge. Potential energy of a single charge is what? Q into VR. I mentioned already once that potential energy of a single charge is basically Q times VR. So, if you have suppose you have electric potential known for a point, and if you take a charge, single charge, and place it at that point, then what will be the potential energy of that charge? So, potential energy of that charge will be V into Q. So, we defined V by potential energy by Q, right. So, this is now we are doing the reverse work, okay, but that is also handy. Some students do not understand it completely, they try to remember it exactly. So, we define V, if you remember, we define V by saying that it is potential energy per unit charge. Now, we are saying that potential energy is basically Q into V, same thing. So, one way or another, but sometimes potential is given, sometimes charge is given. So, no matter what, if you know how can you reverse it, you can apply it and calculate the potential energy. Okay, now, potential energy for a system of charge, when you are keeping 2 charges in a electric potential field, then if you know the potentials, you can calculate using this formula. This is also handy for competitive exam perspective. Okay, so, you can remember this formula. Next is potential energy of a dipole in an external field. So, this is also important derivation. Okay, we have learned about in electric field, when you keep dipole in an external electric field, it experiences a torque, and based on that torque you can calculate the work done, right. In case of normal work done, we know that it is Fx dx, right, F external into dx. Now, in case of torque, it will be tau d theta. okay, because rotational mechanics we are using rotational mechanics, the work done is tau d theta. So, you have to put the p sin theta here and do the derivations. Now, here there will be limits. Okay. Now, we generally choose the starting point is pi by 2, because at pi by 2 cos pi by 2 is 0, that is it. Okay. Otherwise, if for some numerical questions, some competitive exam questions, they might say that it is rotated by an angle 60 degree, a dipole is rotated by an angle 60 degree, dipole is rotated by an angle 60 degree means this theta naught was 0 in that case. So, in that case what you have to do, this is the formula, you have to remember that while solving questions, while solving formula, this is not the formula, this is the formula. So, when it is rotated by an angle 60 degree means initial angle is 0 degree, if nothing is mentioned initial angle is 0 degree. So, formula will be Pe 1 minus cos theta. So, Pe 1 minus cos theta is the formula that you have to remember, but in your book they have chosen that initial angle to be 90 degrees and they have made that at that angle obviously cos theta goes to 0. So, from 90 degree whatever angle you have rotated, that angle is theta, then you get this minus P dot E. Okay, but while doing the derivation you have to do it like that they have done in the book. But while solving questions for competitive examination, only for competitive examination, right, this cos theta will be given as 1, okay, 1 minus cos theta, that you have to be careful about. Now, let us move on. This is the end of today's lecture. Next week we will be discussing electrostatic conductors, and from here on we will complete the chapter. Now, currently if you are aware that we are going through a interesting series called PU2 master blueprint test series, where we are providing you 12 tests, and for focus towards PU board exam, it is currently available for a price of 599 only, and if you add my code SAM100 you will get this only for 499. So, what are you waiting for? Apply this code, the link of this is given in the description, and enjoy this extra 100 rupees bonus. I will be back with the part 2 of this series of this chapter in next Tuesday. Till then, bye.